when you get to know about numbers, the first thing that you perhaps start by doing is adding them, and same holds true for vector algebra as well. So let's add vectors. Let's add vectors today. Adding vectors, and the approach that we're going to discuss right now is using a bit of geometry rather than just diving into straight away just adding numbers up. And an insight that we can borrow from real number addition is that if you have two numbers, and you would add them, so geometrically what you would do is you would mark them on the number line. So if 0 lies here, then you could let's say have this number 3 right here, and to 3 you want to add 2. So you come to 3 from 0, and then you add 2, and let's say you get somewhere here, and you get 3 plus 2 is equal to 5. If you wanted to add -2, even though -2 is represented somewhere here, you still don't care about it. You just assign that number -2 here, and you get somewhere here. You get 3 plus -2 is equal to 1. And you get to the number 1 here. And this same insight that you can actually not only just rely on the fact that where these lines are getting drawn, you can shift them, forms the basis of adding vectors as well. So before even jumping to vectors, let's just take a really simple oversimplified situation. So you start out on your airplane, and using airplane gives you an insight that you don't need to consider any external factors, at least less external factors. And so you just have to zoom through the sky, and having a straight path gives you vectors. So you start from New York City. I'm just cooking up these cities in my head. You start from New York City. From New York City, you go to Delhi. You go to New Delhi. And from New Delhi, let's say you wanted to go to, I don't know, let's say you went to Sydney. And these are not the directions, but just for the sake of drawing vectors, you can always do that. And from Sydney, you went to Washington. From Washington, you went to London. And from London, you went to Los Angeles. And in that trajectory that you had, sort of in your airplane, it doesn't even matter. It doesn't even matter what the sum of whatever the paths you have taken is. As long as you're just getting between New York City and Los Angeles, you're just taking the straight path in between. And so that means instead of going to New Delhi, if you would have taken some sort of off route here, you could have gone to city A, you could have gone to city B, then you would have gone to New Delhi, or you could have just went from NYC to some city A and from there to LA. It doesn't even really matter. As long as the starting and the ending positions are the same, the path that you take to get between those positions doesn't actually affect the sum of those vectors. So given any number of vectors, what you could do is you could just arrange them so that you just get to see the initial and the final position of them. And let's translate this oversimplified situation into some simple vectors. So if you had, let's say, two vectors, vector A, and you had another vector that's, let's call it B. And given the fact that you have aligned, arranged, whatever you want to call it, the head of one vector with the tail of another, as long as you're doing it, you're basically just forgetting this entire path. You just need to take care about the starting position and the ending position, the tail of the first vector and the head of the final vector, and you just join them. So you just join it something like this, more something like that. And once you have done that, once you have joined these vectors, this vector R, whatever you're going to call it, this resultant is equal to the sum of vectors A and B. In some texts, you might get to see this as being called the addition of two vectors being called as the triangle law. The triangle law. And the triangle law really isn't any sort of law. It just, since you get to see a nice enough triangle, you just name it to be a triangle. And you could make any law as long as you want. You could make a heptagon law just by adding 6 vectors and getting its result, and that would just form the 7th vector. And if you want to continue on doing that, and you would see some other term called the polygon law. So if you had a bunch of random vectors laying around, so let's say you have let's make the notation a bit easier. So let's say you have v1, vector v1, then you have another vector v2, then you have some other vector v3, you have some other vector I don't know, v4. You keep on doing this. You have as many as vectors you want to have, and let's say this is vn, and you want to add these vectors. So a thing that you might remember from the previous video is that you can always take this vector and shift it parallelly, and you don't actually change anything. The vector that you get by shifting this vector so that this part right here, this tail, gets aligned with its head, if you shift that, you're not changing anything. And so let's do that. You still would get an equal vector. So let's do that. So you start out by vector v1, and let's draw a really rough representation of that. So you start out by vector v1, sort of, and then you take this vector v2. So v2 would look something like this, really not to the scale. And then you take this vector v3. So you take this tail, align it with the head here, and you just parallelly translate it. So zip, 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 you bring it here, you draw the vector v3. Then you take v4, and again, just align the tail with the head. So something like this. And you could have done this forever, and let's say vn was the final vector, and then you would have something like this. And once you have done that, as long as you're aligning heads with tails, you're alternating that, head, tails, so on and so forth. You just need to consider the first position, the first point, the tail of the first vector, and join it with the head of the last vector. And just join them by this nice vector. Name it any vector you want. Let's name it R for resultant. Then you can see in this case you started out with 1, 2, 3, 4, 5 vectors, and you have 6 vectors which complete this figure, this really rough hexagon. This is not a regular hexagon, but roughly this is a 6-sided polygon. It's a hexagon. You could have extended this argument to, let's say, n number of sides. You could be having a polygon, and then you would have something called the polygon law. So the same thing that you had with triangles, you can generalize that to any number of vectors you want. And so this gives you an insight. Over how vectors really add. And the key takeaway here is that vectors are just representing the difference between positions. As long as you're just keeping in mind that fact, you really don't need to consider any path. And there could be infinitely many vectors that would add up to give this resultant R. You can even just 2 vectors adding, they are infinite, and with increasing number of vectors, that number just skyrockets. But as long as you are just arranging these head tails together, the path really doesn't matter. You can do that in any way as long as you're parallelly translating. Parallel translation is a concept that we built while discussing about equality. Then as long as you're doing that, the resultant vector that you get is actually going to be the same. So this is a very, very brief introduction to how you can begin with vector algebra. And now that we have a rough idea about how vectors add, we really now need to know about what this vector r is. In other words, what is its magnitude? What is its direction? And we want to get some sort of analytic terms for that, not just drawing it on pen and paper. So see you in the next video.